Today we will start Lecture 7-1, Laplace Transform of Circuit Elements. The reading is from Chapter 6 of the course notes, and the objective is at the conclusion of this lecture, students should be able to define the one-sided Laplace transform, redraw circuit elements in the frequency domain, and solve circuit analysis problems using the Laplace transform. As interconnected systems become more complicated, it is difficult to use differential equations to solve for the output. The Laplace transform provides a means to solve differential equations by converting them to the complex frequency S equals sigma plus j omega domain, and then using algebra to determine the output. As I've stated before, we move from convolution in the time domain to multiplication in the frequency domain. The one-sided Laplace transform is defined as x of s is equal to the integral from 0 minus to infinity, x of t, e to the negative st dt. It includes the time 0 minus, the instant before t equals 0, so that we can include the impulse delta of t. The convention for representing the Laplace transform is as follows. X of s is the Laplace transform of x of t, or we use the curly or script L x of t, to convert to x of s. The Laplace transforms can be related to the phasor domain or frequency Fourier transforms by letting s equal j omega. This represents the sinusoidal steady state, which you may have studied in your AC circuits course, but now we use s equals sigma plus j omega because we look at not just the sinusoidal steady state, but also the transient response. Use the definition of the one-sided Laplace transform to find the Laplace transform of x of t equals delta of t. So we're going to have x of s is equal to the integral from 0 minus to infinity, delta of t, e to the minus st dt. Now remember, our property of impulse functions means that this picks off e to the minus st at the value t equals 0. So we get e to the negative s times 0, and the integral from 0 minus to infinity, delta of t dt. So the Laplace transform of delta of t is equal to 1, and we can write this as x of t is equal to delta of t, and the Laplace transform is x of s, which equals to 1. Alternately, we can write this as the Laplace transform of x of t equals 1. Okay, let's try another one. Use the definition of the one-sided Laplace transform to find the Laplace transform of x of t equals delta of t minus t naught. X of s is equal to the integral from 0 minus to infinity, delta of t minus t naught, e to the negative st. You can evaluate e to the minus st at t equal t naught and take it out of the integral. So we have e to the minus st naught, the integral from 0 minus to infinity, delta of t minus t naught, which equals e to the negative st naught when t naught is greater than 0. If t naught is less than 0, then we get that x of s is equal to 0. So we can now say that the Laplace transform of delta of t minus t naught is x of s is equal to e to the negative st naught, which will end up being one of our properties, which is time shifting in the time domain is multiplication by that value in the frequency domain. Let's try another one. Use the definition of the one-sided Laplace transform to find the Laplace transform of x of t equal u of t. So the integral is x of s equals the integral from 0 minus to infinity, u of t, e to the minus st d of t dt, which is equal to the integral from 0 minus to infinity, e to the minus st dt. So by finding that integral, we get negative 1 over s times e to the minus st evaluated from 0 minus to infinity, which equals 1 over s times e to the negative infinity minus e to the negative 0, which equals 1 over s. So one thing we can state is that this is only the solution if the real part of s is greater than 0, because otherwise the integral will not converge. So the Laplace transform of u of t is 1 over s. And we'll do one more. Use the definition of the one-sided Laplace transform to find the Laplace transform of x of t equal e to the minus at u of t. X of s is equal to the integral from 0 minus to infinity e to the negative at u of t e to the minus st dt. You can take the step function out. So that's integral from 0 minus to infinity e to the negative quantity s plus a t dt, which equals e to the negative s plus a t divided by s plus a, evaluated from 0 minus to infinity, which equals 1 over s plus a. And once again, we have the caveat that the real part of s plus a must be greater than 0, because if it's not, then that integral will not converge. So the Laplace transform of e to the minus at u of t is 1 over s plus a. The following table summarizes the relationships between resistors, inductors, and capacitors in the time domain and in the frequency domain. The impedance relationships can be related to the phasor, sinusoidal steady state domain, where s is equal to j omega after the transient has died off, or sigma is equal to 0, and you will see this in your AC circuits course. But in here, we will just focus on the Laplace transform. For a resistor, the voltage-current relationship is that V of t is equal to I of t times R, which is Ohm's law. And in the complex frequency domain, this is V of s is equal to I of s times R, where V of s and I of s are the Laplace transform of the voltage and the current. For the inductor, V of t is equal to L di of t dt, and V of s is equal to L times, and when you find the derivative in the time domain, in the frequency or Laplace domain, that's S I of s minus the initial current I of 0. So there are two ways to represent this in a circuit model. One of them is to show the voltage across the inductor in parallel with a current source with a value of the initial current, V of s equal L times S I of s minus I of 0. Then if you do a source transformation on the left circuit, you get the right one, which is a series instead of a parallel circuit, where you have the inductor in series with the voltage source with a value of L I of 0 minus or L I naught. Now let's look at the capacitor. I of t is equal to C dV of t dt. So in the complex frequency domain, that's I of s is equal to C times S V of s minus the initial voltage across the capacitor. Once again, we have a series and a parallel representation of this model. First, we have the capacitor in series with the voltage source, that is V of 0, the initial voltage over S. When you perform a source transformation, that becomes the capacitor in parallel with a current source with a value of C V of 0. Note that the two frequency domain circuits for the inductor and capacitor initial conditions represent the Thevenin and Norton equivalent circuits with respect to the terminals for those circuits. The relationship between the voltage and current in the frequency domain is also similar to Ohm's law, V equals I times Z, where the impedances are as follows. For a resistor, the impedances are, or admittance, which is the reciprocal of impedance, is 1 over R. For an inductor, the impedance is S times L, or the admittance is 1 over S times L. Or for a capacitor, the impedance is 1 over SC, or the admittance, which is the reciprocal, is S times C. The total system response in the complex frequency domain is the sum of the zero state response, ZSR, and the zero input response, ZIR. The zero state response is the output due to the input only, i.e. the initial conditions are 0. The zero input response is due to the initial conditions only, i.e. the input is 0. The sum of these two yields y of s, where y of s is equal to ZIR plus ZSR. So here we have a loop circuit, which is a resistor, a capacitor, and a voltage source. So the first thing I'm going to do is to redraw this circuit in the complex frequency or S domain. So here's the time domain circuit, and here is the S domain circuit. So we have the voltage source, V I of S. We have the impedance of the capacitor, 1 over SC. We have the initial voltage across the capacitor, which we will represent as V of 0 over S. And we have the resistor here, where we call the output, the voltage across that resistor, V naught of S. So if we define a clockwise current around this loop as I of S, V naught of S is equal to I of S times R. But we have two voltages here. So we know that I of S is equal to V I of S minus V of 0 over S divided by R plus 1 over SC. So when we solve for V naught of S is equal to R over R plus 1 over SC times VI of S minus R over S times R plus 1 over SC times V of 0. And remember, the zero state response is the one due to 0 initial conditions. So the zero state response is SCR over SCR plus 1 times VI of S. The zero input response is the one due to no input. So this one is negative RC over SCR plus 1. Let's look at another one. Find the output V naught of S for the following circuit and identify the zero state response and the zero input response. Remember, the circuit on the left is a parallel circuit, and it's the time domain circuit with the current source I of t, V naught across the parallel combination of the resistor, the inductor, and the capacitor. So in the S domain, or the complex frequency domain, we're going to have the current I of S, the voltage V naught of S, the resistor R, the capacitor 1 over SC, and this time we're going to represent the voltage across the capacitor in terms of the parallel current source with a value of C times V of 0. Then we have the inductor SL, and we have the current that represents the initial current through the inductor, which is the arrow pointing down, I of 0 over S. So since we have a single node pair circuit here, we can do KCL, where ground is defined to be at the bottom. So I of S is equal to V naught of S over R plus SC V naught of S plus V naught of S over SL plus I of 0 S minus C V of 0. Using algebra, we can rewrite this equation as V naught of S times the quantity SL plus S squared LRC plus R is equal to SLR I of S minus LR I of 0 plus SLRC V of 0. And now we're going to separate this into the zero state response and the zero input response. So V naught of S is equal to SLR I of S over S squared LRC plus SL plus R, and this term represents the zero state response, plus SLRC V of 0 minus LR I of 0 divided by S squared LRC plus SL plus R, and this entire term represents the zero input response. Okay, let's use the following switching circuit for our final example for today's lecture. Find the output V naught of S for the following circuit and then identify the zero state response and the zero input response. We're going to do this one a little differently. We're going to actually draw the initial conditions and the input and then use that to find the zero state response and the zero input response. So first of all, we have a switching circuit where the switch moves from position A to position B at t equals 0. So we use position A in order to find the DC conditions. So at position A, we have the steady state. At position A, we'll have the steady state output voltage for the capacitor based upon having an open circuit, and we have the 8-volt source and the 2 ohm resistor. So what we see here is that V naught of 0, the voltage across the capacitor, is equal to 8 volts, and I of 0, the current through the inductor, is equal to 0 amps. So that's the time domain circuit. So the frequency domain circuit after switching would look like the following. The one for 0 initial conditions is just going to have VI of S, which is equal to 12 over S. And we're going to have the 2 ohm resistor, 1 over SC, the capacitor, which is 5 over S, and then SL for the inductor, which is S. And then the output voltage would be V naught of S. So the zero state response, V naught of S, would be equal to 5 over S divided by 2 plus 5 over S plus S times 12 over S. And this is the zero state response. This can be simplified also to be 5 over S squared plus 2S plus 5 times VI of S. For the zero input response, we turn off the input, and now we draw all of the elements and their initial conditions. So we have the 2 ohm resistor, we have 5 over S for the capacitor, we have 8 over S, which represents the voltage source with an initial voltage for the initial voltage across the capacitor, so that's the same as V of 0 over S. And then we have the inductor, but there is no initial current, so we just have an S here, and then V naught of S would be the voltage across those two. To find V naught of S, first we're going to define the current I of S. So if I of S is a clockwise current that flows this way, then I of S is equal to V of 0 over S divided by 2 plus S plus 5 over S. And we get that V naught of S is equal to negative 5 over S I of S plus V of 0 over S. And when we simplify this, we get that V naught of S is equal to negative V over 0 over S squared plus 2S plus 5 times 5 over S plus V of 0 over S, and this term represents my zero input response, And now to find V naught of S, we just add these two terms together. So the complete answer is V naught of S is equal to 5 over S squared plus 2S plus 5 VI of S plus S squared plus 2S over S times the quantity S squared plus 2S plus 5 times V of 0. And now we put in the values for V of 0 and the value for VI of S, and we get V naught of S is equal to 5 over S squared plus 2S plus 5 times 12 over S plus S squared plus 2S over S times S squared plus 2S plus 5 times 8. And we're going to stop here, but this motivates what we will talk about next, which is using inverse Laplace transforms in order to solve for V naught of t. And this concludes today's lecture on circuit analysis elements with Laplace transforms.